Good morning, everyone. It's my pleasure to be here, and I'm honored that I've been invited as the first speaker uh, of this activity. So I'll be talking about forest carbon accounting based on remote sensing. Uh, Hopefully, I can finish the presentation on time, but we'll see. We have a lot of things to. I have a lot of things to talk about. Would start with a short research bio, and also I'd like to share with you my activities in the BSP program. So I also, of course, give you context first about forest carbon emissions and also in relation to climate change. Talk about remote sensing and how it's the go-to tool to map biomass and carbon. Talk about spatially explicit carbon pools, so not just the above ground component, but also the below ground component, the soil, and also some minor carbon pools like deadwood and litter. Talk about carbon accounting scales, very important. Could be national, subnational, could be a reforestation project. Carbon changes and fluxes mapping. So it's quite the state of the art now in terms of remote sensing application to map the changes itself, not just static or baseline maps. Very important, the UNFCCC carbon accounting framework and the SIA framework, two of the biggest frameworks for carbon accounting. Number 8, uncertainty sources of carbon accounts, another important topic. And of course, I'd share some practical side, data, open data, tools, emerging tools, platforms for carbon accounting, and of course, we'll end up with outlooks and synthesis. So, I'm relatively a new researcher slash scientist also. I've been publishing since 2021 mainly because of my PhD. So my research interests more on RS applications, also GIS. I've been GIS specialist also in the past, but now it's more on like a RSAI application to to solve environmental problems in general. But I'm more particular in the application of EO, RS to system accounting, carbon accounting, and also I'm into digital agriculture, also climate smart farming also to the Leeds Agri. And I founded a research NGO, Impact R&D, to also amplify the social impact of research, not just the scientific side. So let me just share some pictures of my phase 1 BSP engagement. So it was like last December, was my phase 1. It was a lot of lectures, workshops, and research. What I enjoyed the most was like sharing really my expertise especially to the students and young professionals. So very fortunate in that sense. Now it's also the last activity of my physical activity of my phase 2. So I'm happy to do it here. Yeah, so I'm expected also to publish papers after the engagement and stuff. But my BSP is helping also Reinvest Project 2, which Doc Isa will talk about later. Also, so my entry point are, of course, the geoinformation remote sensing requirement of the project. It's a natural capital accounting, system accounting project in West Philippine Sea. So it makes me more interested in that sense. And I think we should really use environmental R&D to help strengthen our conviction that it's ours. Yeah, first, some side pictures. So what we see, of course, are trees being cut, forest burning, forest being converted to most likely agriculture and also mining. And also in the coastal ecosystem side, so we see mangroves being cut for charcoal production. This is in San Vicente, Palawan. Mangroves being converted for fish pond land use, and also seagrass being degraded. So what also happens is that with these deforestation degradation activities, carbon and eventually carbon dioxide also is being emitted in the atmosphere. And of course, mind that CO2 is a greenhouse gas. So the GHG is being trapped, of course, in the atmosphere, and of course, it causes global warming. And this has also driven arguably the biggest environmental challenge of our generation, which is climate change. And of course, because of climate change, the world's ice are melting, sea level is increasing, typhoons getting stronger and also unpredictable, dry spell, and so on. So you've been experiencing it. I think also now it's a sign that these this temperature increase also, this weather is also perhaps climate change driven. To help combat climate change, the ideal scenario is to, of course, to reduce the deforestation, hopefully degradation also, by protecting the existing forest. And of course, we should also plant more trees. We should also restore degraded forests. Of course, the younger the trees, the more carbon it sequesters. And it lessens, of course, the carbon in the atmosphere. So this role of the forest can be monitored and measured through AGB, or above ground biomass. So see, AGB is since carbon is half the weight of AGB. So in particular, AGB can be measured from above. It can be remotely sensed thanks to the satellites above, as you can see in the diagram also, and also in the from the field surveys. So in situ, and also so we have ground-based and space-based data sets to requirements to map AGB. So above ground biomass and carbon, this should play. This should autoplay, but just imagine it's playing. Yeah, so the mapping of AGB before was primarily for timber production, for forest productivity estimates. But in the past few decades, it's well, the mapping rationale is that surveys itself can't do it alone. So we need to have like a practical approach how to have large area estimates, mapping and estimates also. Ever since, it's literally considered an essential climate variable, or ECV. This is, of course, a very crucial variable to understand the Earth systems and in its relation to the climate change. So we can't continue talking about mapping without talking about remote sensing, or RS. So by definition, it's the acquisition of information of objects or phenomenon. So think about this object as a tree, or a phenomenon as a land use change from a distance. So you need a sensor, a camera, a special camera, a sensor that's mounted on aircrafts, UAVs, drones, satellites. So it's a signal-based interpretation of Earth's surface, depending on the reflected. You can see on the graph. Let me just check if I can. Yeah, so reflected and the energy, the light energy emitted from the surface. So yeah, so yeah, there are remote sensing windows. These white windows here, and the way sensors capture the emitted or reflected energy it depends on that window, and specific sensors can capture specific signals or energy. So we basically have optical sensors, and you're familiar with it. Of course, our camera phones operate on the visible window here. But we have like the invisible light, so special sensors capture that, and there's some unique characteristic of about that signal that our camera phones can't detect. So we have, I can highlight, it's on my next slide, but I can give an overview now. Of course, there's these multispectral sensors. Yeah, there's thermal sensors, there's radar sensors also, and there is LiDAR sensor also. And the way the sensors capture it depend on the wavelength and the frequency of that So by definition, you might hear about, you may probably heard about Earth observation already. So EEO. So it's basically simply just satellite-based remote sensing. So it's more of the satellite taking pictures of the planet. So that's a European definition, because in Wikipedia you might see that ground-based observation of Earth also is considered EO, but uh, take the European definition because of some. Uh, so EO, okay. So just to highlight also the sensors I've been talking about. So optical, you see on the left side, you see several bands. These are called remote sensing bands. We're familiar with the visible light, the RGB here, but as I said, there's like other more bands that can give us more information about the surface. Could be something about the health of the plant, the vegetation, something about the structure, something about the differentiation between land covers, and so on. So on the upper right, you can see some depiction of a radar sensor. So as I said earlier, it depends on the wavelength length. So those shorter ones can just simply detect the top of the canopy, like C-band, X-C-band. But some other longer wavelength sensors, radar, can penetrate the canopy and give us more interpretation of the forest. So these are like the biomass-friendly sensors, like L-band and C-band and P-band. And of course, there's LiDAR, which is like this nice picture color-coded, nice color gradient. So yeah, it's basically a point cloud out of point clouds from LiDAR is a laser as a sensor also. It gives us point clouds, and also at the end it gives us a forest structure indicator like height, and height we can derive biomass from height. Yeah, it's also called the ranging sensor. So you may common sensors, LiDAR sensors, of course, the ISAT-2, built for measuring, sensing, mostly the boreal regions, and of course the GDI. GDI is like the more tropical forest-oriented satellite mission. So radar, of course, you might heard about Sentinel-1 already, ALOS Pulsar, and of course the optical ones are the most common, Landsat, Sentinel-2. Moving on, giving more context about how these different sensors distinguish land features. So that's the beauty of remote sensing signals, the way how we differentiate one thing to another. So in this case, it's like basically grass, soil, water, and also even forest types. So here we see coniferous and deciduous forest. And on the upper right graph, it's a backscatter from radar sensor. It's a backscatter signal that differentiates forest types also very clearly. And also on the upper and the lower right, you can see it can distinguish as detailed as forest species. So I'd like to emphasize also that we're in the RSEO golden era. So it's a lot of satellite missions being implemented, being operational. There's a bunch of satellite missions also dedicated to measure the forest in the coming years. So we have the biomass first P-band mission on space by ESA. Not ESA, but European Space Agency. And what's more interesting is that, it's more of like the commercial side, but there's like some satellites are getting smaller. And now there's this CubeSats that like a very tiny satellite that's flying around and dedicated to measuring specific things. So big EO data cubes, also like the new format now for these remote sensing EO data sets. So you can see it on this. So it's like more of like a time series EO data. mhm, differentiated, of course, spatially, temporally, also spectrally. So yeah. Okay, so AGB or carbon mapping based on remote sensing. Of course, it's in a way it's like easy to think. It's like RS signals. So you have the pixel value of remote sensing images, and the surveys and the in situ surveys you saw earlier. The plot biomass. So from as outputs of forest inventory, for instance. So we measure DBH, we measure the tree height, and then we estimate. We also measure wood density, and we estimate biomass from data using allometric models. So we relate the level biomass to the remote sensing signal, basically. And what we get, yeah. So this was yours truly, 10 years ago in San Vicente, Palawan. Uh, so the plot level biomass estimate is being related to the, well, when I say related, there's like a regression model, for instance, with the remote sensing data. And then we have like a regression model to predict biomass for each pixel after that. So it can also be like a exponential model in this case, where we relate plot level biomass to backscatter values. And yeah, so that also was my methodology when I mapped the PubCount biomass and of the Philippines using nonlinear regression model, machine learning based model. I use the NFI from DNR-FMB and both optical and radar images, also to have like a nonlinear regression model that was able to map biomass at spatially explicit at nationwide scale. So, like given data availability, you can also like do an intermediate step, which is estimating biomass at local scales. When I say local scales, it could be 200 by 250 meters. Could be a bit bigger. So what drives it? There are airborne LiDAR surveys that are available mostly in the topics. So given that, the plot level biomass is first related to the airborne LiDAR metrics. So we have a local estimate that's like really locally calibrated. And that's super important. And then that locally calibrated points are then related subsequently to the remote sensing data. So we have like a large scale map. So NFI, for instance, and then should go ahead. NFI, for instance, and then local airborne LiDAR maps surveys. So we were able to map local scales, and then remote sensing data, and then we have a large scale, in this case, pan-tropical map. And that methodology was used by the benchmark biomass maps, Achi and Bassini maps. So, and then another methodology, it should play, but I think I should. This one is the GDI biomass map from, of course, GDI spaceborne LiDAR. So it's like it's like it came from the biomass was derived from height. So height was first derived from the point clouds and yeah, it's the forest.
Tracks 600 meters apart, with 25-meter footprints every 60 meters. That's 968 footprints per second. Laser energy traveling almost 300 million meters per second reflects off higher surfaces first, then lower surfaces shortly after. The tiny delay is detectable by JEDI's telescope sensor, which records the intensity of the reflection over time and uses the known speed of light with other variables to calculate a waveform documenting the reflective density of the footprint at various elevations, representing the surface below. Users can process these data into maps illustrating ground elevation, canopy height, and other surface characteristics. What's new in version 2?
Hello. Yeah, so GDI map is one of the most commonly used maps also from EO. EO is an EO product. So it also follows a rigorous sampling methodology in estimating biomass at pixel scale. So I should have posted the GDI paper link here, but yeah. Okay, siguro one more note about the GDI map. So it treats the footprint as the in situ data. No? So yeah, and they have designed these sampling rigorous sampling framework to they implemented rigorous sampling framework to estimate biomass at pixel scale. So next is the CCI map produced by European Space Agency. So GDI was NASA and then ESA is CCI. CCI is yeah. So some maps can be estimated without the calibration data or the in situ data, the ground data. So it can be the biomass value can be derived directly from the remote sensing pixel. In this case, some backscatter value of ALOS pulsar, and it's because of some ready-made physical equation already that's been around for decades. So in this case, the authors have used the water cloud model to and fulfilled the parameter requirements to be able to map biomass at a hectare scale. So I was also involved in this paper. Okay, so I've been talking about the above ground component. So might as well talk about the other components, the other carbon pools. So of course there's below ground, there's soil organic carbon, there's of course the deadwood and litter carbon pools. So mostly they're biomass dependent. So the above ground component dependent. So we mostly estimate these four carbon pools from the biomass using in the case of the BGC using root shoot ratio, which so for deadwood and litter they use like the IPCC estimates, also suggestions that you apply some proportion based on some weather, climate characteristics, and also depends on the forest region So I'm also working on a paper that tries to spatialize, so to create 5 carbon pools map out of EO datasets. So yep, and we also try to expand the study and do the carbon accounting using the two accounting frameworks. And then these are like, would like to share a preliminary finding, so don't post it. So yeah, it's basically the C pools breakdown of from the 6 country cases, including Philippines, of course. So I'd like to highlight the relevance and applications of the C pools map, not just the above ground component, but the C pools map. So mainly it's used for the global scale application. Number one in the list is it's used as an input to the climate carbon models and climate models of to understand the Earth system more, project climate change better, etc. So I'd like to share also the survey we did 2 years ago, asking the climate modelers about the data requirements, and they were asking about we'll be happy if you give us time series biomass at least kilometers spatial scale. So yeah, most of them. Yeah. So before they were like just asking for a baseline map. Now they're asking for like really a time series. So of course it can be more dynamic, the model, and can have somehow integrate trends also in their projections. But, second would be the IPCC guidelines for national GHG inventories. The document, as thick as this, it's published online also. And there's this tier 1 estimates, mean biomass estimates per distinct for forest strata. Forest strata defined by many may multiple factors also. But we're also trying to have EO-based estimates equivalent to the Tier 1 estimates from using the GDA and the CCI. So it's an ongoing, it's a paper under review also. Collaboration with a bunch of international scientists. What's the relevance of this? That countries without data sets, without NFIs, for instance, relatively less developed countries can rely on these estimates for their national reporting. And of course, the global carbon budgets, the generic carbon report budgets that's being updated every year. So that also the biomap, global assessments also using biomass maps also matter in that case. And then there's these national applications, which is can also categorize this based on how countries report. So countries are mandated to report the UNFCCC, especially those who signed the Paris Agreement. So it's technically called as NDCs, nationally determined contribution of countries to track the commitment to reduce emissions from carbon emissions. And in this case, from the LULUCF sector. So there's also the RED Plus, or these reducing emissions from deforestation, degradation projects. Been around for almost a decade or so, and it's like more focused to these local, regional scale projects. So it's tied up also to the people on the ground that if they were able to restore the forest and manage it, they'll be incentivized. So that's the project. Okay, so later on I'll discuss the two big frameworks, the SIA and the UNFCCC, and perhaps compare them. But for now, let me talk a bit about ecosystem accounting, which is the synonymous mostly to SIA. It's an international statistical standard, last 2021, but it's been around for almost a decade already. It basically gives us a guideline how to implement carbon accounting, so as the nature, the ecosystem services will play a role also in the economic picture of the country. So its motto is making nature count. So what the two main requirements are, of course, and also linked to each other. Of course, the physical accounts, which you can see in the upper part, and also the physical accounts can be made in the context of carbon accounting, can be provided by the biomass and carbon maps, for instance. The ecosystem service part can be also provided by dynamic carbon maps, or if you consider change maps, which I'll talk about later also, it can give an indication of the carbon sequestration of forests also, which is an ecosystem service. And then you have, like on the lower part, the monetary accounts, where you apply some monetary valuation methods to quantify the ecosystem service. So in other words, it's like if you're rich in natural capital, ecosystem service, are also, of course, a wealthy country. And people will be happy, and the well-being will, prosperity will be assured. So that's the context. Okay. Yeah. So as I said, system accounting NCA is mostly complemented by remote sensing, earth observation, mainly because ecosystems are large spatial features. So you need to do the accounting per ecosystem, like mangroves, broadleaf forest, coniferous forest, and so on. So there's like a typology followed by UN, like the IUC and global typology in terms of the ecosystem classifications. So you do the accounting usually periodically, usually annually, every 5 years also possible. And yeah. There's also an ongoing community. The communities was organized 2 years ago, and now it's very active also. So the EO for EA community, and I was able to talk also last year with regards to this EO EA context. Okay, so this is also quite important. The accounting scales. So you do carbon accounting, of course, globally. As I mentioned earlier, in the global carbon budgets. So it's like a big table of carbon account. What goes in, what goes out. What's the net flux in the bio carbon pool. Yeah, and also an example of that is this table on the lower left, on the left side, disaggregated per ecoregion and also per forest age, forest type, sorry. And of course, you can do carbon accounting, of course, nationally or subnationally. I think it's also a clear requirement also of the carbon accounting frameworks that you do it at the national scale, subnational scale also. And of course, there's these ecosystem levels estimates, carbon accounting, which is imposed by SIA, of course. Common spatial scale for SIA carbon accounting framework. So maybe I can talk a bit about the table. So in the lower right, you can see ecosystem types. So you see an opening forest hectare, the opening stocks, 2010, I think. And then you have like a column of the emissions. We were able to disaggregate emissions from deforestation and degradation in this case. We have sequestration column also, of course. And of course, when you subtract emissions and sequestration, you have net flux. If it's negative, it's bad. If it's positive, it's good. It's green. Then you have the closing forest hectares, so closing tax. So, okay. So the column over there on the right, that's the UNFCCC format. So it's mainly it's limited on the anthropogenic activities. Later on, I will also highlight the differences and similarities of the two frameworks. Okay, so going to the more on the small scale, local scale, regional scale carbon accounting. Okay, so one example is of course the RED Plus program. So yeah, an example map input for the RED Plus is the one playing in your screens right now. So in that case, we were able to map carbon emissions at high spatial and temporal resolutions, which is requirement of these local projects, RED Plus projects. And it also plays a role in the voluntary carbon market. Wherein carbon credits are, of course, there's a Lazada of carbon credits from these projects. And maybe you heard about the term carbon offsetting. So companies can buy these credits and also finance reforestation projects, for instance. So, and the way to monitor, report, and verify these kind of projects, of course, EO plays a big role. So in the transparency context. So, yeah. So an input to these, to be able to have inputs to the carbon accounting tables in terms of the changes, the fluxes, the emission, the sequestration. You need we need to talk about changes, fluxes of carbon. So seas change fluxes mapping. So in general, there are two approach. One is simply to difference two maps from two different periods. And you have a sea flux map at the end, which is exemplified by the map, the CCI map, and also the LVOD map. And you can also use a baseline biomass, like biomass year 2000. And then you can have an activity data. You have forest loss and gain maps also, or information with corresponding emissions and sequestration default. So like if it's a forest fire, this is the emission. If it's a conversion to slash and burn, this it's also forest fire. But if it's like agriculture conversion, this could be the emission. So it's being used. It's being updated like depending on the activity data that you have. So you can imagine a yearly carbon flux map and accounting table because of this approach. So yeah. Okay, so an example of a stack change approach. So you can stack change can also be differentiated whether it's a direct mapping or indirect mapping. So indirect mapping involves two maps that you subtract, and you can also directly map C fluxes if you have the data. For instance, if you have remeasured research plot or remeasured NFI or remeasured local maps from airborne LiDAR. So if you have repeated measurements, you can simply you can already produce a biomass change from that, and you can already relate that biomass change to remote sensing data and have a C flux map at the end. So here you see some examples of the 5 countries. So green means sequestration. You have net sequestration over the last decade. And so imagine the power of these maps. You can see hotspot maps where the emissions, where the sequestration. So we chose to do it directly because there's some. It's known that when you do the indirect mapping, you subtract one map from another, the errors also sum up. So there's some statistical consideration also in that case. So I did some ensemble machine learning for this, meaning maps from different spatial predictions of different machine learning maps were harmonized to have one map at the end. So that's like also the state of the art now. People are confused. Adrian's using random forest, and the other one is using SVM. One is contented with linear regression, and it's hard to assess them. So let me just make the average of them and have one map at the end. Okay, so this is like the big slide. UNFC, CC, and CF frameworks. So both are UN frameworks. Both measures ecosystem flows, like of course sequestration, emissions. Where do the carbon stocks go? Yeah, as I said, UNFC is limited to anthropogenic activities only. Lulu CF, CS more EO dependent. I would say, and it follows like an ecosystem typology. But common thing about them, aside from the flows, is that both are not explicit about reported uncertainties. So if you see, normally the carbon accounting tables doesn't have like a plus minus okay, confidence interval, for instance. So that's also a big development now in the carbon accounting context, and I'll talk about it in the coming slides. So reporting carbon accounts uncertainties. What's commonly practiced is that I'm talking about the countries here who are participating to the RED Plus project of UNFCCC. So either they're not reporting the uncertainty, zero, no plus minus number, or they report the wrong uncertainty. So the estimation method is has loopholes or needs improvement. Yeah, so first one is sadly practiced by most system accounting efforts also, and also and well, some the RED Plus, because they've been around for decades already. The MRV system is more advanced, more mature. So what are they doing is that when the estimates of emissions and emission reductions and payments are reduced if uncertainties are high, assuming that the uncertainty estimates are robust or correct. So they also penalize the partners if they have, like, they're unsure about the carbon accounts. So say it like that. In other words, if the confidence interval, for instance, are really wide. I should talk about the common map error, not only in biomass map, but in most environmental variables, which is like the signal saturation problem. So as you saw earlier also, the signal can only penetrate at certain wavelengths, cannot penetrate the the canopy. So you see flat line there. You consider one forest and another, especially if they're contiguous, the same, because uh, especially in high and very dense forests. And that results in map underestimation. So maps typically underestimate the high biomass part. So of course, that's the bulk of your biomass, your carbon. So you're already underestimating it. And that might be resolved by, like, of course, when you fly like a longer wavelength sensor like P-band, the biomass mission, the LiDAR also mitigates that problem. Because of course, as you saw, that it can really have a nice waveform of the tree, structure of the tree. But these kind of problems, as we assess it, 4 maps, including the benchmark maps, suffer from this map underestimation. And we were able to say so because of the map assessment exercise that we did. So the independent validation that we did is also part of my PhD. So we have a global set of reference data. And we also were super strict about the reference data side. We know for a fact that they are called ground truth, but they are not error-free. So you also should take that into consideration, estimate the uncertainties at the plot level, and after that, you can have a more meaningful comparison between plot and map estimates in validation context. So some errors can be from as early as the measurement stage. If could be a human error, could be an equipment error, it could be from the allometric model. So that should be counted. Pixel size and also the plots can have spatial mismatches, so they are not fit. They have usually plots are smaller, and they can be surveyed from different years. Also, there's also temporal mismatch. So and also geolocation. So there's a bunch of uncertainty sources, and you need to account that when you're doing validation to assess map accuracy. What we did also was to, given this information, we see an underestimation and we have a global distribution of reference data, we were able to map the bias itself, the error itself, as a function of different environmental variables. So we got a map bias, we simply subtract it to the original map and we have a bias adjusted map after. So it's a function of tree cover, biomass itself, and also topography plays a role because these sensors like radar, of course, are topography sensitive also, and of course moisture also. But topography plays a role also. And if you want to read more, I can share the link also. Another important one is it's really common to see a lot of estimates from maps. A statistical estimate like a total or a mean or over large areas. And when you do that, you're technically doing a model-based approach, inference. Yeah. And it's when you do existence accounting, you cannot escape this uncertainty source. When you're doing spatial aggregation, you need to account for spatially correlated map errors because they don't cancel out when you aggregate. When you create a total, we can create a mean over the Philippines. What's the mean biomass? What's the total carbon? You need to account for that. And it's clearly shown in this diagram that weak spatial autocorrelation, you have narrower uncertainty, confidence interval, for instance, and with strong spatial correlation in this part. So, yeah. Okay, a few more slides. This is also important. Maps are products of samples of the, for instance, of an NFI, a research plot. You create a map out of that sample. It's also a sample. NFIs are usually sampled under probability distribution functions. So it could be stratified, an output of stratify, a sample of a a stratified random sample, as sample from a random sample, a systematic one. So it's more of it's good if it's that if it's sampled like that, but if not, you can encounter problems also. That's what we call purposive sampling or ad hoc sample. So it most likely it will undersample, or it will misrepresent your study area, as exemplified by the red ones. So these are the areas in the features, environmental feature space, meaning that's what you underrepresent considering the forest variability and how forest strata are made, should be considered. So in other words, that's the red part should be the part that you should sample. And there are ways now to really assess it efficiently, conduct some representativity analysis. The first bullet one is more complicated. For instance, Philippines would want to have carbon account submitted next year to UNFCCC, and we will rely on the CCI map, for instance. So we should consider, because the first one, the previous slide was talking about uncertainty from residual or map error, autocorrelation, residual variability. And this one is from sampling variability, and it dominates the error budget at national scale and larger. So, but this nice publication highlights the need for map makers to produce this in their metadata, sampling covariance matrices, mainly because a sample can give you many kinds of maps or many variants, a multiverse of map. So, yeah, that should really be communicated at least. So, last few slides, forest area inconsistency. So you should also be cautious about this. There's a lot of forest definition. This one is from Estoque et al. Showing different forest cover in the Philippines. And this is also from a study saying differentiating forests reported from the different carbon accounting frameworks. And this also relates to my ongoing study with the interim team. We're trying to compare 11 mangrove maps, so you can see it here. You can see immediately a large standard deviation here, 8,000 out of the 26,000 mean hectares. So that's something to think of when we try to choose or an ecosystem extent map for our accounting purposes. So this was like 8 global sources and 3 global sources, including the NAMRIA maps. Okay, let's talk about the local setting, Philippine setting. So let me share that ecosystem accounting was piloted 9 years ago to the Waves project, and I was fortunately involved in that project. From there on, several big projects also popped up, like this Cebol, the Reinvest 2, of course. And what's more interesting is the third bullet, which is the PENCAS is now officially a law, just a month ago, I think. So Philippine Ecosystem Natural Capital Accounting System Act has been passed. And then there's ongoing compilation, of course, of official EA accounts by respective institutions. I think there's also an ongoing NFI cycle, and of course our mapping agencies and will play a big role. Of course, we have PILSA already. If USA has NASA, we have PILSA. So, okay, enablers of RS-based carbon accounting. There's really a steep development progress in this context. You see map viewers, online map viewers that you can easily produce carbon accounts in few clicks. You have computing engines designated for these purposes, system accounting. One is like this Open Earth Monitor. So I'm also part of this project in my postdoc. So, and also this exercise that's trying to harmonize the global maps to create a better one. So this was the right part of the slide. You see like a map and some tables. So I'm playing around with the RR Shiny tool to quickly create carbon accounts out of EO maps. So there's a lot going on, a lot of things going on, a lot of developments, a lot of upcomings. This one is like we're preparing for the biomass mission next year. So yeah. So it's really more on like how to make this bunch of maps meaningful and, if possible, harmonize to serve a higher purpose. Another important slide. I was talking about the upcoming missions. There are more. NASA will launch NISAR, an L-band mission. There's Landsat next, which will increase spatial temporal resolution of the Landsat mission, 10 meters and 6-day repeated cycle, I think. And MAP mission, which is the hyperspectral satellite mission. So hyperspectral means we have more bands. We can see more, basically. We can see if plants are sick, or we can distinguish one species to another quite easily compared to multispectral. Countries are increasing its capacity to conduct NFIs and to produce their own reports also. So countries are also repeating their NFIs, so meaning we will have data sets for change, biomass carbon change. And I'd like to highlight also that the space-based and the ground-based can be integrated to produce a better estimate. So that's, I think, the state of the art now. It's not just map, it's not just NFIs, but the integration of the two really produces a better estimate or a better carbon account, for instance. And that has been highlighted by this study, which I was also fortunately involved. So what can we expect in the coming years? There's this 3-level carbon mapping, which is also a subject for debate in terms of usability and practicability and other things. There's TLS, of course. TLS has been around for decades now, but it's still very useful, and it's like really the most accurate option when we try to measure the forests on the ground compared to like the manual forest inventory. And there's this very interesting mobile laser scanner, and what's captured my attention the most also is this mobile app that can easily tell you us about the DBH in this case. So imagine if this can be operational, the inventory can be super fast. Okay. My last slide, and it's also I'm over time. I'm 10 minutes over time, I think. Just to wrap it up and also give you something to think also after this. So RS-based AGB carbon accounting, climate change context. So before it's mainly for production, for forestry, but now it's more encompassing environmental problem. I'd like to emphasize the second bullet, which is we should really think about uncertainties. It's easy to make a map, it's easy to make an AL model, but how sure are you, how reliable is that estimate from your model? You can simply report a high R squared, but is that true? Or is that a pseudo R squared? Or is your model overfitted? That's why it gives you a high R squared. So yeah. And map assessment, it's like a collaborative exercise. It also gives the map producers feedback. And it also leans toward harmonization exercises. So space-based and ground-based integration. One example was the bias reduction method I showed. There are other more things like more rigorous, statistically rigorous approaches. You can note about design-based estimates, inferences. You can note about model-assisted inferences, hybrid inferences. So this one, I mostly showed you about model-based approaches because it's more of like a global setting with using a sample of non-probability-based sample. So, carbon accounting framework comparison, so UNFCC versus SIA, and also the role of these online data repositories, computing platforms to speed up and also have more convenient MRV for especially for national and local projects. So yeah, thank you for listening and happy to discuss things with you. Okay.